the reminder is. Okay, I just sent out a reminder on Slack as well for students. Um, yeah, it's my pleasure to have Katey Anthony Walter here today, who will talk about permafrost thaw and methane release from Arctic lakes. And a lot of you might have seen some of her work already, and kind of on the more popular channels on TV, where she's done a lot of work and outreach in that domain, but has written a couple of kind of more fundamental papers on the methane dynamics in high Arctic ecosystems. And we actually met her once, at least at times where GPS was still traveling around, to say that there is something like a GPS field trip. Last year it went up to kind of the Alaska area and traveling basically up to Dead Horse with a couple of SUVs, so to say. And these are some pictures here where we met Katey near Fairbanks at a lake where she's actually studying methane emissions. So this is the whole group at the top left here. Students probably hated me because they suddenly had to go through muddy waters, and we almost lost Dan in there because he got stuck in the mud and was really hard to pull him back out again. But this is Katey here giving us a little explanation on how the kind of permafrost dynamics and these thermokarst systems, the methane dynamics work. And that was a really great talk directly in that environment, because Alaska is, for me, it was the first time being there. It is a special landscape, and I'm really, really happy to have her here talk about this important topic. Just to give a little bit of a background, she actually did a BS in Mount Holyoke, I don't know how to pronounce it, Holyoke College,
Mount Holyoke, yeah.
Holyoke College in biogeochemistry, with actually a minor in Russian studies. This kind of piqued my interest. You being now in Alaska, you not only have kind of foreign policy experience by just seeing Russia, but you actually put the work in trying to learn about Russian studies. So this is an interesting fact. Also relates probably to permafrost, that will help you kind of study the entire range of high Arctic ecosystems a little bit better. Actually went on to do a master's at UC Davis, so that's not too far away from where we are right now, and a PhD at the University of Alaska in Fairbanks, where she also did a postdoc and is faculty member. So basically got stuck in the beautiful place in Fairbanks, Alaska. And with that, I don't want to steal much more of your time, but I'm happy to hear you talk about permafrost thaw and methane release from Arctic lakes.
Thank you, Christian, and everybody else for inviting me. I will share my screen and get it into a mode. Okay, so today I will be talking about ancient methane emissions from thermokarst lakes in past, present, and future methane budgets. Permafrost covers 24% of the northern hemisphere, so that's looking down at the polar view on the left-hand side. And it consists of ice. This is a cross-section, a photograph of a cross-section of a Siberian river. I did live in Russia actually in 1992, before the internet, when the Soviet Union had just fallen apart, as an exchange student, and really fell in love with Russia. So it would be hard to say whether it was science or Russia that pulled me into the Arctic. It was both. And I spent a lot of time during my PhD in Siberia. So it's the fondest memories probably of discovering so many things that you get to do as a PhD student, and also being in Siberia. So many of these photos will be from Siberia. So permafrost by definition is ground that's been frozen for at least 2 consecutive years. And it doesn't have to be ice. You could have frozen bedrock. But what we're really interested in is ice-rich and carbon-rich frozen soils. Because permafrost contains a huge pool of soil organic carbon, 1,400 to 1,600 gigatons. And that's equivalent to about 150 years worth of current anthropogenic fossil fuel emissions. So the question is, what's the fate of this ancient carbon? Much of it has been locked away from the atmosphere for thousands of years. What will happen to that ancient carbon as permafrost thaws? And the soil carbon then becomes food for microbes that generate greenhouse gases, which cause more warming and more thaw in what we call a permafrost carbon feedback. The potential for old carbon release to the atmosphere has been implied from laboratory incubations, where scientists go out to permafrost and sample it and bring it into the laboratory and put it in jars and measure how much carbon dioxide or methane can be generated. And they find that, yes, old carbon can be readily converted into greenhouse gases. People have also gone out to ecosystems and manipulated them by warming them and seeing that in that situation, you can measure the release of old permafrost carbon. However, without manipulation, just going out and measuring these sort of environments where permafrost is naturally thawing, in a terrestrial landscape like this, people are having a hard time measuring old carbon dioxide, or old methane. And the reason for that is that as permafrost soils thaw and that active layer gets deeper, nutrients are released that enhance plant growth. And so as permafrost is thawing, we're actually seeing a response of plants growing and absorbing carbon dioxide out of the atmosphere and building up soil organic matter instead of a net loss. And so as a result, permafrost carbon models, many have projected that it will not be until well beyond 2100, so 80 years from now, that we will see really significant large losses of old permafrost carbon. The problem with most of these permafrost carbon feedback models is that they're missing processes that we know are important. And they're missing them because they're heterogeneous processes. They're processes that are not easy to put into the models. But some of these include abrupt thaw and geologic methane. So abrupt thaw is important because it thaws permafrost much more efficiently than gradual thaw. And thermokarst lakes are the most common form of abrupt thaw. Once you get standing water on the landscape, it really speeds up the thaw of the ground beneath the lake. So it's orders of magnitude faster than just gradual deepening of the active layer. And yet we've known now for decades that these thermokarst lakes are emitting ancient methane and ancient carbon dioxide. So the radiocarbon age of methane coming out of these lakes are on the northern Seward Peninsula in Alaska, the peninsula that juts out across from Russia. 14 to 43,000 years old is the methane in the bubbles. So the points that I'd like to talk about today is that if we include abrupt thaw in models, it will double the permafrost carbon feedback this century. Abrupt thaw is the most efficient means of releasing old permafrost carbon. Abrupt thaw accelerated when climate warmed 14,000 years ago. It's accelerating now in some regions, and it will likely continue as climate warms in the future. However, over longer timescales, these abrupt thaw lakes actually change from a net source to a net sink if they're given enough time. And it's basically because you're opening the freezer door and the carbon that was locked up in the freezer decomposes and gets mineralized and turns into greenhouse gases. And then the microbes run out of that ancient carbon source. And so then those environments instead can turn into a net sink. Geologic methane, so methane trapped in and beneath permafrost, that's not just produced by microbes today. It occurs, but it's not well known how much is escaping. And I think we have some really new, exciting remote sensing methods that can help us resolve discrepancies in the Arctic methane budget. So we're looking again at a polar view of the Arctic, and about 20% of the permafrost region is ice rich. It has a large volume of ice, which makes it susceptible to thermokarst. When the ice in the ground melts, the ground collapses, and if you have a poor drainage system, then that water ponding begins thermokarst. And here we're looking at a special kind of permafrost known as yedema. It formed in extensive areas of Siberia and other parts of North America, or Alaska and Northwest Canada, during the last ice age, when much of Europe and North America was covered by glaciers. There were refugia that were not glaciated, and those were the ecosystems that supported the mammoth and the woolly rhino and Pleistocene lion, and they were feeding on a really productive grassland ecosystem. And as those animals lived and the grasses grew, there were very high sedimentation rates from glaciers elsewhere in the world. And so you had sediment being deposited, and grass is growing, and a permafrost table that was rising with that sedimentation. And so not very much time went by before the grass roots were frozen in place, and they never went to the stage of humification. So we have very labile carbon in this ice age permafrost soil known as yedema. And it's very deep, thick permafrost soil. So when that Yedema thaws and the carbon starts to decompose, you can generate greenhouse gases pretty readily. And Stanford Alumni Magazine depicted it this way. So it's not surprising that those Yedema permafrost soils formed during the last ice age, 14,000 to 60,000 years ago. And the radiocarbon age and the methane that we're seeing bubbling out of lakes today, when those lakes thaw, that Yedema permafrost matches the age of the soil, 14 to 43,000 years. In the same types of lakes, we also measure the radiocarbon age of carbon dioxide, and it's a lot younger. And the reason is that carbon dioxide primarily escapes lakes by diffusion because it's such a soluble gas. Methane is semi-soluble and more readily comes out as bubbles. A very large unknown in this permafrost carbon modeling, and I'm saying this to graduate students who might be looking for a topic that needs to be tackled, is how much, when permafrost thaws deep beneath these lakes in what we call a thaw bulb, how much of that organic matter goes to methane and how much to carbon dioxide? We don't know the answer well. When we've taken those soils in the laboratory and incubated them for a long time, a year, or Christian Noblock did it for 7 years, we see that methane gets produced in excess of carbon dioxide. So many models are using, for deep permafrost thaw, a 1-to-1 molar ratio. However, Sergei Zimov, who was my mentor in Siberia, he said, Katya, there's no carbon dioxide produced at depth beneath these lakes. It's all methane. And that's hard to reconcile stoichiometrically if you don't have an external hydrogen source. But recently, people who work in glacial environments have shown that fine-grained glacial sediments, which is what Yedema really is, let off hydrogen. And so it could be that there is much more methane produced in excess of carbon dioxide than we know about. And the last winter, I was out on the edge of a lake. I don't know if can you all see my cursor? Nod your head if you can see where I'm pointing. Okay, so I put a chamber down last spring on the margin of one of these lakes, and the thaw bulb extends out adjacent to the lake. And in March, when the ground should be frozen, really high rates of methane were coming out of the ground, and some carbon dioxide too. I radiocarbon dated. So we're on land. We're not even talking about water. We're on land next to the lake. The methane was 38,000 years old. The carbon dioxide was 300 years old. So it was coming from a crack in the ground that extended deep down into the Tallik, not passing through a water column. And it was almost all the ancient carbon was methane with no carbon dioxide. So I think, I'm not going to talk much more about this tonight. I'm just going to leave it out there for people who are looking for a really important topic to work on. And that is really how, when permafrost thaws in a deep environment, how much goes to methane and how much goes to carbon dioxide. We have also looked at the radiocarbon age of dissolved methane. So if you were to go out and take a sample of the lake water, not the bubbles, but the water, and radiocarbonate the methane in the water that's dissolved, it's a lot younger than the bubbles. And that's because that methane is diffusing out of surface lake sediments that have a larger component of young carbon. Plants that have recently died and organisms that live in the lake are mixing with old carbon. So the bubbles are being plumbed. They're channeling the release of greenhouse gases from this really deep thaw environment. And if we study dissolved gases, they are showing us what's diffusing out of sediments, and it's a lot younger. So lakes bubble. Bubbling is the dominant way that methane escapes lakes. And if you were to go out to a lake in the summer, you could watch these bubbles rise up through the water column and pop and go into the atmosphere. But in the winter, the lake surface freezes and ice grows from the top down. So as bubbling continues, the lake ice actually traps the bubbles. It's like a time-lapse photograph of ebullition. And if you were to go out and poke a spear into these bubbles and light a match, you would get a flame like this, because methane is a natural gas and it's flammable. And the methane you see in this plume here is about 3 weeks worth of methane from one of those bubbles. So if we consider that each lake has thousands of methane bubbles and that there are millions of lakes in the Arctic, then it becomes an important question: how much of this ancient methane is being released today? And so one way that I've studied this ever since I was a graduate student is to go out and shovel the surface of lakes and then map the density of ice-trapped methane bubbles, and I've classified them based on their morphologies. So the A-type bubbles have the lowest bubbling rate, and you get sequentially higher bubbling rates as you go into B-type, C-type, and then hot spots bubble enough to actually prevent the ice from freezing. You get ice-free cavities. We also open the ice over these bubbling points and lower funnels down to the bottom of the lake. And the funnels today we have wired to tip rain gauge tipping buckets. We've just taken a rain gauge and turned it upside down underwater. And so as the bubbles come in, they cause the buckets to tip. And then that the tipping events get logged on a Campbell data logger. So we can get the year-round bubbling rates associated with these different ice bubble patterns. And then just to confirm that our data are accurate, we also chainsaw out blocks of ice and look at the volumes of gas that get trapped in the ice over the course of winter. And we've done these approaches on getting close to around 300 lakes around the Pan-Arctic in different climate and permafrost regimes. And another thing that we've done is quantify how much carbon is in the soil next to these lakes so that we can quantify what the soil carbon erosion rates are. On the right-hand side, the red line is the 1952 shoreline, and then the image shows a more recent shoreline. So this lake has expanded. And as it's expanded, we know if we've quantified the carbon in the soil, we know how much carbon went into the lake by thermokarst expansion. And we can compare that to the methane emissions that we're observing coming out of the same lake. And when we do that, here we're looking at thermokarst soil carbon erosion on the x-axis and methane bubbling on the y-axis. And we see that the amount of methane bubbling out of lakes is directly proportional to the amount of soil carbon coming into lakes. And we've looked at that not just for Yedema type thermokarst lakes, but for other thermokarst lakes that are formed in non-Yedema environments. And non-Yedema environments are typically Holocene age permafrost soils that you get on the Alaska North Slope. So the people that went on that Dead Horse field trip would have gone through extensive areas of non-Yedema permafrost. And then even glacial lakes that formed because of glacial processes. Around those glacial lakes, the ground is frozen, and those lakes are expanding today by thermokarst as well. We also saw that the radiocarbon age of the methane in the bubbles had a 1-to-1 relationship with permafrost soil carbon age. So what was very interesting, the Yedema lakes had the oldest soil carbon and the oldest age, and then the Holocene and non-Yedema lakes had the youngest carbon. What I'd really like to point out though, is that no bubble that we've ever measured from a natural ebullition event has modern carbon in it. It's all old. If you go out and you take a stick and you stir sediments, bubbles will come up. Or if you step in the mud, bubbles will come up. But you are disturbing the sediments and you're inducing ebullition, and then you can get modern ages. So stirring and disturbing sediments is a false way of radiocarbon dating natural ebullition. And natural ebullition is C14 depleted. So how much abrupt thaw is taking place today? One way that we can answer that question is to use high resolution aerial photos and satellite images to see how lake areas have changed. And so this is this lake here is the lake that Christian came out to for his field trip. And this is in Goldstream Valley. It's a Yedema region in Fairbanks. And what that valley looked like in 1949, it had very few lakes. And over the years, new lakes have formed and existing lakes have expanded. And what we've observed actually is close to a 40% increase in lake area in this region. In spring of 2016, we flew a helicopter with EM on it, and we're able to map out the distribution of permafrost and how deep the thaw bulbs are beneath these new lake features. And we found that some of these new lakes could have over less than 60 years thaw bulbs that had grown to be 10 or 15 meters deep. So really rapid thaw compared to what you would get in a gradual thaw environment where you just have active layer increasing in the absence of standing water. So how do the greenhouse gas emissions compare between gradual thaw and abrupt thaw? Here we're looking at net ecosystem exchange, grams of carbon dioxide equivalent per meter squared per year for gradual thaw sites in Alaska and abrupt thaw sites. So abrupt thaw, because it's so much faster, it's thawing permafrost so much deeper and faster, there's a larger volume of soil that's being decomposed. And so that as a result, the emissions are much higher. than they are in a gradual thaw environment. We also see that the age of the greenhouse gases, carbon dioxide and methane, being released from abrupt thaw is much older than gradual thaw. And that makes sense. Abrupt thaw is tapping into deeper, older carbon sources than gradual thaw. So how important is abrupt thaw to the permafrost carbon feedback? To answer that question, we compared methane and carbon dioxide emissions from an abrupt thaw model to methane and carbon dioxide emissions from the CLM land surface model. And what we found is that abrupt thaw lakes will double the permafrost carbon feedback this century. We did this for RCP 4.5 and 8.5. And we found that the impact on this feedback is actually higher for RCP 4.5 than 8.5, and that methane became the dominant driver of that permafrost carbon feedback. So our modeling only looked at Thermokarst lakes, but more recently Merritt-Turetsky led a synthesis study where we included not just Thermokarst lakes, but also Thermokarst peatlands and retrogressive thaw slumps, other modes of abrupt thaw emissions. And she concluded that looking out to the next 300 years, 40% of permafrost carbon region emissions will come from abrupt thaw, but abrupt thaw sites would only occupy less than 5% of the area. So that leads us to believe that these abrupt thaw sites are hotspots of permafrost carbon emissions. However, the theory of permafrost carbon feedback has recently been questioned. And it was first questioned by really neat study done out of Rochester, Vas Petrenko's group, where they were able to take large volumes of glacial ice in Antarctica and measure the radiocarbon ages of what would have been atmospheric methane back through time. So on the y-axis, we're looking at 18,000 years ago to 8,000 years ago. And in panel C here, that's the atmospheric methane concentration. So there were periods during the last deglaciation when the concentration of atmosphere abruptly increased. And people don't know the source of that increase in the northern hemisphere. So they postulated that if that abrupt increase in atmospheric methane was coming out of permafrost or methane hydrates, older sources of carbon, then the radiocarbon age in the ice core should have gotten older, but it didn't. It didn't get older by very much anyway. And so they concluded that, they concluded that during that time, there was a global warming of 4 degrees Celsius. And that's about what kind of warming we might experience in the future under RCP 8.5. So if in the past, warming did not result in a permafrost carbon feedback, they suggested we don't have anything to be concerned about for the future when we have 4-degree warming. There's a big difference though. The 4-degree warming in the past happened over a 8,000 year period. And right now the warming is happening over an 80-year period. So it's not the same environment. Their conclusions, though, that there's the permafrost carbon feedback is nothing to be concerned about, was corroborated by a number of studies where people went out and they measured methane and carbon dioxide in Thermokarst systems and found that it was contemporary carbon dominated by young carbon. But these studies were mostly measuring dissolved gases. They were looking at the ages of the gas in the water, which we already looked at. I've incorporated their data in. It's young carbon because it's diffusing out of younger sediments. So I compiled all of the radiocarbon data I could find for Thermokarst lakes for Yedema and non-Yedema type systems and for carbon dioxide and methane. And what I found is that Yedema systems are constantly emitting older carbon than non-Yedema systems. Methane is older than carbon dioxide, and bubble ages are much older than diffusion ages. And so it's not a surprise. There's diversity on the landscape. We have young permafrost soils and old permafrost soils. And depending on where you sample and what you're sampling for, it seems to me we're getting pretty systematic results. So by compiling all that data together and then weighting it by the contribution of ebullition versus diffusion for these different lake types, I came up with a integrated radiocarbon age of methane coming out of all Pan-Arctic lakes today, and it's 2,800 years. In the ice core model from Petrenko's group, they didn't know the age of permafrost carbon emissions, so they used a placeholder of 7,800 years. And with that older age, they found that their model could allow during deglaciation anywhere from 7 to 18 teragrams of methane per year coming from permafrost carbon sources of a 7,800 year age. So our group has done a fair amount of modeling of deglacial methane emissions from Thermokarst lakes using a very different approach. We have gone out to those permafrost bluff exposures, and we've dated the birthdays of when lakes formed throughout the Holocene. We've cored modern lakes, but we've also gone to ancient lake basins and radiocarbon the base of those basins to find out how long ago was there a lake in that place. And so the bottom graph here is looking at lake basal dates, the birthdays of lakes from 18,000 years ago to present. 18,000 years ago, we're coming out of the last glacial maximum and very, very few lakes were forming. However, when climate warmed abruptly 14,000 years ago, and then we had the Younger Dryas, climate cooled and lake formation slowed down, and then climate warmed again abruptly at 11.6 thousand, we saw a Thermokarst lake formation response. The formation of lakes responded to climate warming in the past. And our model, if we apply estimated methane emissions to the distribution of these basal dates, we come up with, it's a bottom-up approach, and we come up with Thermokarst lakes emitting anywhere from less than 1 to 11 teragrams per year. So it fits just fine within the constraints of the polar ice core modeling efforts. And we've actually taken but we know that the radiocarbon age of methane today is younger coming out of the lakes. It's younger than what the ice core modelers were using. So we are working on a paper with them now incorporating the younger age. And what it shows is that, yes, the ice core model and our paleo record estimates of methane emissions are in full agreement. And lakes did form in response to climate warming in the past, and permafrost will thaw as climate warms in the future. I would like to show, though, that the feedback in the past, here we're looking at permafrost carbon emissions versus time with time on a log scale. So the amount of carbon that came out of permafrost in the past, it was pretty small compared to what's expected to happen in the next 80 years. And I think it's because there was a much more gradual thaw in the past compared to what we're expecting to see this century. But to put permafrost carbon emissions into context, our models suggest that 1.5 to 4.2 gigatons of carbon dioxide equivalent per year will be released from permafrost carbon. Compare that to fossil fuel emissions in the present day approaching 40 gigatons per year, and that is expected to rise. So permafrost carbon emissions are much smaller, at most up to 10% of anthropogenic emissions. However, once you open the freezer door, there's only that carbon will be released. And so even if people we're able to cut fossil fuel emissions back to the RCP 4.5 scenario, there's still a significant amount of permafrost carbon that will be released and acting as a headwind against further mitigation efforts. A big unknown, though, in our modeling and predicting the future is, as permafrost thaws, how much of it will be an anaerobic environment or an aerobic environment? If we were to wind the clock back 20,000 years before Thermokarst really happened, this landscape you're looking at would be a lot flatter, and it would not be as well incised by lakes because the lakes melt the ice, and then when the lakes drain, they result in a landscape with a lot more relief. So if a new lake were to form right up here on this upland today, it could not become a huge lake before it would tap into a drainage gradient. And so our landscape relief today is very different than it was before. So how much of it will be wet or dry is a question that also needs to be looked at. And I think another great project for a student could be to take a digital elevation model and just populate it with new lake formations and see how much area could the landscape actually hold in the future. So we often hear that we're losing lakes in the Arctic, and that's true for a lot of regions. And so if we're losing lakes, then what's the impact on the permafrost carbon feedback? Well, it really depends on the ratio of the gross lake area loss versus the gross lake area gain. Because even in places where we're losing lakes, we can still be forming new lakes. And it's the forming of new lakes that matters most. Here I'm showing the carbon fluxes associated with just a terrestrial environment. That represents tundra or boreal forest. So there's a small sink of carbon dioxide and a small emission of methane. If you form a lake for the first time on that landscape, then the resulting carbon dioxide and methane emissions are huge. So the delta change in flux forming a lake results in a lot of net emissions. In contrast, if you have an old lake sitting around on the landscape that's already used up its old permafrost carbon and it drains and forms a terrestrial environment, the change in flux is a lot smaller. And so you might have a lot of lake drainage happening with a smaller change in flux, but what's really important is the ratio of drainage to lake formation. And what we found is that until the area of lakes draining exceeds the area of lakes forming by 7%, we will continue to have a positive permafrost carbon feedback, even in regions where we have a net lake area loss. Okay, now I'm going to change topics a little bit and talk about a different role that lakes play. And so far we've talked about how they contribute to climate warming. But as lakes sit around and get old on the landscape, they actually switch roles and they become climate coolers by absorbing CO2 out of the atmosphere and building peat in the bottom of lakes. And I became interested in this as a graduate student, driving up and down the rivers with Sergei Zimov, studying permafrost exposures. And what I noticed is that here, it's like the river cut through an ancient lake basin. So if you see, it looks a little bit like a cereal bowl. That's where the lake was before the water drained out. And what I saw was just these really thick bluffs of red peat moss coming in the permafrost. So it wasn't all Yedema, there was a ton of moss. And we got out and climbed up in there and pulled this material, and it was almost like spaghetti noodles. It was very poorly decomposed, had a lot of integrity, beautiful red bryophyte peat. It's the brown mosses that grow in the bottoms of lakes. And we can see those mosses growing in present day lakes too. They love the nutrients. They love this environment of permafrost thaw. And so to quantify how much carbon these lakes have actually soaked up out of the atmosphere over time, this is up here in Northeast Siberia, and we traveled up the Kolyma River and went around to different exposures of ancient lake basins. And we sampled what the carbon stocks were in these basins. So the x-axis is the quantity of carbon per square meter of the ground. And then we did that for 50 different lakes in the tundra and boreal regions. And what we found, the average of all of that Siberian ancient lake carbon stock data, is that these North Siberian lakes have accumulated more carbon faster, especially given the cold environment in which they occur, than other lakes, other northern lakes and peatlands, which are all the other data points. So why is it? What is it about these thermokarst lakes that makes them such strong sinks for atmospheric carbon dioxide? I think there's 4 things that are happening. First of all, when you form a lake, you have all of the tundra and boreal forest ecosystem that's falling into the lake and contributing to sediment carbon. Then nutrients are released into these lakes, which promote the growth of aquatic plants and mosses. And so the thawing permafrost is actually fertilizing the lakes and stimulating plant growth. These lakes are very deep because the ice goes so deep into the ground, and so they stratify. And the bottoms of these lakes, I measured, a lot of lakes get to be 4 degrees Celsius because that's the highest density of water, but a lot of these lakes in Siberia, I measured 1.5 degrees or 2 degrees Celsius. And they had a huge amount of DOC in them. So it's probably the density of dissolved ions combined with this permafrost environment that was a very cold anoxic environment, which really slows decomposition. And then finally, when the lakes drain, their thaw bulb, talik, refreezes. And so permafrost forms again and preserves all that carbon. And so if we look at the life cycle of a thermokarst lake, we have to ask, well, what are these lakes? Are they net warmers or net coolers? The top panel is showing permafrost before you have a lake. When lakes are first born, for the first centuries, they are huge emitters of methane. They're also releasing carbon dioxide. But once that permafrost carbon source gets used up, and if the lake doesn't drain away, it switches roles. And then it goes into a later mature lake stage where it's absorbing carbon dioxide. So today, most of the lakes on the landscape actually are a net cooling, having a net cooling impact. And it's really only the margins of lakes that are new or new lakes that have formed that are big sources. And so you can't just take the fluxes from any lakes. It really matters if it's a young lake or an old lake. So what about the future? These models are projecting huge emissions in the future. And that's right. If we have a lot of new abrupt thaw in the future, then we can expect that red line to be true, that the permafrost carbon emissions, we're standing on the threshold of much larger emissions than anything we've seen for the last 10,000 years. Okay, the last topic I'm going to talk about is geologic methane. We often hear about methane hydrate and large geologic gas sources. So what are those and how much methane are they emitting? They are not included in the climate models. I first became interested in them when I was recently hired at the University of Alaska as a young professor. And I'm sure all of you too, you start studying something and you get a reputation. So my grandpa wrote me a little cartoon sketch, which is still posted in my office. It says, Katey Walter, the gassy lassie, methane queen of the Klondike. And so with a reputation, the phone rings and people want to tell you their weird methane stories. And so one time the phone rang and I got a call from people who knew that there was this methane seep near Barrow. And it was outside of the hunting cabin of an elder Inupiat woman. And it had been there since she was a little girl. And it sounded interesting. So I went up and looked at it. And what I saw was this. Just a tremendous amount of bubbling. And that bubbling is this is that seep. That was much stronger than anything I had ever seen. And my jaw dropped and I wondered, is that a decomposing mammoth or this has to be a different source of gas? And so it turns out that this is actually coal bed methane that is streaming up through thawed permafrost beneath this lake. Let me see how I can get out of here. Go on to the next one. So I wanted to quantify how many of these geologic methane seeps are out there in the Arctic. And the way that I first went about it was just to get in little airplanes and fly around after lakes had frozen and looking for places where the water was open. And I saw things like this from the airplane. And then I got on the ground, you can see some pictures here, and walked up and just looked in those holes and confirmed that they were bubbling, and then sampled the gas, and then radiocarbon dated it and looked at its stable isotopes and other hydrocarbon ratios. And the black line shows the flight path of where we flew. And the yellow dots are places where we found these really large geologic methane seeps. The green dots are just places where we did our ecological methane work. And what I found is that these geologic seeps, the geologic is shown in black and the ecologic in white, the bubbling rates associated with them were up to 7 orders of magnitude higher than ecologic methane. The radiocarbon dates of these geologic seeps were mostly fossil. The stable isotopes of the geologic seeps showed either thermogenic or a mixture of thermogenic and microbial. And I would point out that in Alaska, a lot of the natural gas is actually microbial methane formed from coal beds. So microbial can be geologic, fossil. And then I also saw that the ratio of methane to ethane and propane in these gas bubbles, just naturally coming out of lakes, matched those Bernard ratios that the USGS had measured in actual gas wells. So deep sourced natural gas is bubbling up to the atmosphere. And then I saw that not just in the permafrost environment, but also down in South Central Alaska and Greenland, in places where glaciers have been receding since the Little Ice Age. And we first did the field work and the aerial surveys, and then later I got a map of the faults. And it was really interesting to find out that if the gas coming right on top of one of these neogenic faults was thermogenic methane, and as you moved away from faults, it became more of a mixture of of thermogenic and microbial. So came up with the hypothesis of a leaky cryosphere cap, and other people have hypothesized this too, that permafrost can form an impermeable layer or a semi-permeable layer. I don't think it's perfect because there's unfrozen water content. And we're seeing these geologic emissions in places where we know the talik does not penetrate to the bottom of permafrost. So, but permafrost, it makes sense that it impedes the flow of this deep gas. In glacial environments, because the bottoms of glaciers are warm, it's really the mass of the ice, that overburden, that is putting a stress on the ground. And as you remove the overburden, it activates joints and faults associated with isostatic rebound. So it lets this deeper trapped gas escape. And what we saw was that down in that glacial environment, there were actually many, many more geologic seeps than in the Arctic, but they were each one was a lot smaller. And I'm thinking, I'm not a glaciologist, but I'm thinking that's because the timing of that cryosphere cap was a lot shorter. We've had glaciers advance and retreat on more frequent time scales. So they're trapping gas for longer, for shorter, than you get in the permafrost zone, where permafrost can be 2 million years old. So the cap in the Arctic is older. It's been trapping gas longer. And where seeps are coming out up here, they're huge. Each seep has very high emissions, but there are far fewer of them. So the total amount of methane coming out, geologic methane coming out, is unknown, but it does constitute an additional feedback. Many of us have seen these blowout pictures from Siberia, from the Yamal Peninsula region. And recently in Alaska, here in Northwest Alaska, we worked in a lake that's only 1 meter deep. But we found in that lake, it's actually the largest known terrestrial methane seep on Earth at the moment. I think there's another one in Indonesia, but it's still being debated in the literature. But currently, for the short time period, it's the largest known seep. And the morphology of this lake was not exactly like the Yamal craters, but a lot like it. The lake was 1 meter deep, but then where these large gas plumes were coming out, it dropped down suddenly 45 or 15 meters with very steep margins. So we may have some of those types of features also occurring in Alaska. Our current estimate of geologic emissions, I think, is very conservative. It's 2 teragrams per year. So the principle of how SAR works is that it's a radar beam that is interacting with the ice water interface under the ice sheet. Because the bubbles have an insulating effect, the ice sheet does not have a uniform thickness. Where you have bubbles, you have thinner ice, and where you don't have bubbles, it's thicker. And so the bottom of the ice sheet is rough. And that radar beam has backscatter, and where you have more bubbling, you have brighter backscatter, and where there's less bubbling, less backscatter. And so we've created a regression line and applied that to 5,000 lakes in Alaska, and found that we could map the methane, we could estimate methane bubbling. We had a beautiful relationship between field work and satellite remote sensing to estimate the methane emissions from these individual lakes. And what we found is that until now, all of us who do field work, we go out and we measure whatever lake we come to, and we get a methane number. And then we multiply that emission by all the area of all the lakes in the Arctic. We've been overestimating methane in the Arctic from lakes, because we tend to go to smaller lakes, and smaller lakes have more methane. So another great thing about using remote sensing is that it removes a lot of that bias. It looks at every individual lake, and it accounts for the contribution from these large lakes that have lower emissions. So with that, I'll conclude that abrupt thaw doubles the permafrost carbon feedback this century. Contrary to recent statements, abrupt thaw does release old carbon, but you get what you sample for. There's definitely young carbon in the system too. Abrupt thaw is not new. It accelerated 14,000 years ago when we went out of the last ice age and into the current interglacial. It's accelerating now in some regions, and it's likely to accelerate as climate warms in the future. Climate cooling also occurs after lakes get old. Geologic methane is a wild card, but I think remote sensing has some really exciting opportunities to improve and reconcile some of these questions that we have about the methane budget. And with that, I'll thank you. Take any questions.
Thanks so much, Katie. That was a wonderful talk. It was also interesting when we were there and going up to Dead Horse, the oil fields there, they are pretty gas rich and they actually have to pump out gas that would almost power the entire US, but they have to basically pump it back in because they have no way of getting rid of it because there's only an oil pipeline and the ships can't go through the whole year. So that it is an interesting area, but I don't want to take up any questions on my own. Are there any questions from the audience? Students first, or people who raise their hands, Jess and Preston.
Go ahead, Preston.
Thank you for a very interesting talk. My question, if I understand correctly, is that your findings were that the long-term behavior of the lakes is to be a carbon sink once they've sort of oxidized the carbon that's initially present. And maybe I misunderstood that, but I'm surprised that they're net sinks as opposed to sort of netting out to zero. And I was hoping you could talk a little bit more about why it is that the sign is what it is.
Well, oops, we have some feedback. What we did is we looked at the carbon accumulation rate. So we looked at how much peat carbon is in these basins on top of the thawed permafrost soils, and then radiocarbon dated it through that sequence to get the carbon accumulation rates. And then I compared that to how much, and both the timing and the magnitude of permafrost carbon that was lost when the lake first formed. So if we go out to a permafrost bluff that has never thawed, you still have intact ice age permafrost, it's about 2% organic carbon. Then if we go to permafrost that thawed under a lake, and then the lake drained and that permafrost refroze and measure how much carbon is there, we find out that 30% of the original permafrost carbon was lost beneath the lake. And so that kind of mass balance approach lets us calculate how much permafrost carbon over the life of a lake escaped to the atmosphere. And we can compare that to how much carbon is sitting there in lake sediments and peat in the same sequence. And we find out that over time, you actually, over the course of the lake's life, it accumulated more carbon than it lost. Does that answer the question? So these lakes are still emitting methane and carbon dioxide, but they're depositing more carbon and building it up in sediments more than is being released. For old lakes, that's not true for new lakes.
Thank you. We have Jess and then Erica Podest and then Hannah next.
Thanks, Katie. That was really interesting talk. You covered a lot of ground. And I'm going to rewind you a little bit to one of your slides where you were showing the basal radiocarbon ages for lakes all around, I can't remember if it was Siberia and North America, but around the Arctic. And you highlighted the start of the Bowling Alrod and the end of the Younger Dryas as two abrupt warmings, where there were also more lakes. But it looked to me like there were like almost periodic, with about a 2,000 year period or so, little bumps in the whole record, that there were many more little minima there, as if something else is working in the background besides the attribution to these abrupt warmings. I just wonder what you thought about that.
Well, I think I've looked at that and wondered about that too. So he's talking about these little bumps. First of all, we don't have a huge number of ages. One of my students is about to put out a new paper where we've increased the number of ages, but for Thermokarst lakes, I want to say it's still under 200. So the reason it looks like there's a lot is we've taken we've binned around the uncertainty on each of the basal dates. So I think what's happening, what we're seeing there, so it's not we need more data to really fill it in, whether we trust those humps or not. It could be that it's possible that we're seeing at the landscape scale, drainages and lake formation sequences, because a lake really, I mean, many of them can sit around for 9,000 years, but a lot of them drain after 3,000. Then permafrost reforms for 1,000 years, and then you get a new lake forming. So we could be seeing some of that general pattern.
Yeah, I was
that without a lot more data.
Yeah, well, I don't know. Like that looks pretty statistically significant to me. You've got N, if that's N on the y-axis on the left there, you know, anyhow, it feels like maybe you're catching their time scale of, back to Preston's question, right, of the full lifetime of the lakes, right, and when they have what sign, and that's operating in the background, and it was just this climate forcing, right, of these abrupt warmings that did something to whatever's controlling that process to amplify it either over a wider area or, right, because it seems to have kept the same inherent timescale. And then that should be marching right through the modern, right? Like that. And
yeah, so the modern, we have
really about being amplified with modern warming.
One question I hate getting is, is Thermokarst lake formation accelerating? Because we have two different sets of tools that don't match up. We have this paleo approach where the number of basal records from recent times is really too small for me to feel confident. So is it increasing in the paleo record? It's really hard to say. So our tool for saying recent changes is remote sensing records, but those only go back 60 years. So without a lot more effort to increase that paleo record, unless we can think of a new way of understanding kind of what's been happening for the last 200 years with lake formation rates, to my mind, that means paleo work, or a combination of paleo and modeling. But yeah, there could be, we have not looked really carefully at how that cycle, because this is, as you said, these are lakes across Beringia. And so the climate dynamic was spatiotemporally variable. But maybe there is an underlying pattern there. It looks like it. I've wondered about it.
Thank you. Erica?
Yes, this is Erica Podest. Thanks for that great talk. I was wondering if you've also looked at the horizontal transport of carbon and how much of that DOC ends up in the ocean?
No, I have not. But it's an important question, and the DOC work that's been done finds old DOC coming out of these systems. Certainly some, if your lakes are hydrologically connected, then there would be transport out of them, as well as methane and carbon dioxide. But it's a lot of what I'm familiar with has been done in rivers. And there again, it really depends. It's the same as with lakes. The age of the soils that your river is draining reflects the age of the DOC that's coming out for the most part.
Great, thanks.
Thank you. Hannah, go ahead.
Yeah, thank you so much for this really interesting talk. Especially, I thought it was interesting to see the wide variety of methods you're using to really get at those flux values. I am interested in methanotrophy, and so I've started to be really curious about the interactions between methanotrophy and methanogenesis in the environment, and how sometimes higher levels of methane production can also promote higher levels of methanotrophy. And I'd be really curious if you have any either findings or just suspicions about methanotrophy in and around these thermokarst lakes.
I have a great curiosity. I've had a few students dabble in it, and I think it's an area that needs a lot more work. And for one of the reasons is that the organisms living in these lakes, if you take a chironomid or a plant that's growing in the lake, they will often have an old age. So they are using up old carbon. And the way that they're getting that old carbon is through methanotrophy. So I think we don't know well the role of it and how much it's responsible for, but I suspect that as climate warms, so one important thing that happens is as that ice sheet traps the bubbles in the winter, the methane actually leaves the bubbles and it goes into a solution in the water column. And so now, because bubbles by themselves are not accessible to microbes, but once they sit under that ice in winter and the methane goes into solution, now they are. And so the role, how much of that methane escaping bubbles is being consumed by microbes, I think is a really important question that needs to be looked at. What system
really interesting.
Are you working in? Yeah.
What was that?
What system are you working in?
Well, Woody and I are just sort of starting to spin up a project, but we're really curious about methanotrophy in soils sort of throughout the Western US. And we're actually planning hopefully some work at one of our field sites in Alaska too. So.
Okay, well,
Thank
come
you.
up to the lakes and dabble there too. You'd be welcome.
Sounds great.
So in a way, these bubbles are basically bypassing any chance of undergoing kind of methanogens on the way out, right? Methanotrophs on the way out. It's similar to like the plant-mediated emissions in rice paddies, where usually if you have to purely diffuse through soil, then there's often very little methane that actually comes out, but these more fast events like ebullition or mediated plant transport might actually speed that up quite a bit.
Yes, so the sediments are so dense that methane is not diffusing through them. It's escaping through bubble tubes. And that's why we get that repeated bubbling in these point sources. We have drilled down to the bottom of the talus and cored the sediments, and then looked at the isotopes in the sediment core and compared it to the free phase gas that comes out of that drill hole that's left behind. And the free phase gas is very isotopically depleted, suggesting that it has not been oxidized. But the pore water methane is heavy, really heavy. So, and we measure anaerobic methane oxidation in the system. So definitely methane that's dissolved in the sediments is being subject to anaerobic methane oxidation, but the bubbles are bypassing it. So that free phase is protecting that methane from oxidation.
Great. Thank you, Jörn. I think we are at the hour now. Thanks so much for your talk, Katey. Thanks for